So we are going to determine here the critical load. As I have mentioned, in structural steel, you are already given the dimensions, you're already given the structural members. All you have to do is to choose whether that particular sections are sufficient enough to support the loads. Or in this particular problem, what we are going to do is to find the critical load, meaning how much load can be carried by this particular section. So since you are given the properties of this section, a wide plan section for a column, we are going to determine the critical load. And accordingly, we can use the formula of Euler's critical load. So we can make use of the formula for Euler's critical load. According to Euler's critical load, Euler, the Euler's critical load, P sub C, is given by this formula. It's simply F, or force, critical force, and then you multiply it by the area, A. Okay. And then if you are going to determine the stress from the basic formula of stress is equals to load over area. But in the formula for Euler's critical stress, this one is critical load. This is critical load. But if you are going to determine the Euler's critical stress, FC, this is critical stress. You're going to determine the critical stress. We will have this formula, F sub C, which is equals to pi squared E all over KL over R squared. Wherein the value for K depends on the condition of the end support. So in this particular case, since the column is a wide plan section with hinge at the bottom, the value of K here that we are going to use is equals to 1. Again, the value of K is dependent on the end condition of the supports. So according to our problem, it is hinged at both ends. So since it is hinged at both ends, we are going to use the value for K is equals to 1.0. There are other conditions wherein the end conditions state that the end conditions free, fixed to rotate at one end, fixed to translate at one end. So that means you have a fixed condition for both ends. That is has a value of 0.5. But if the end condition is free at one end, free to rotate at one end, but it is fixed to rotate to translate at the other end, then we have we can have the value for 0.7, condition 0.7. So for hinge, we have, if both ends is hinged, we have the value for the effective length factor K is equals to 1.0. And L over R is the slenderness ratio. Again, the slenderness ratio is the ratio between the unsupported length and the least radius of gyration. So if you are going to use the least radius of gyration, since there are two radius of gyration presented in the properties of the section, you're going to choose the least of the choices. The value for E is the modulus of elasticity. And of course, you have the constant value of pi. So if we are going to determine the slenderness ratio, KL over R, take note that this is the maximum slenderness ratio. We are going to use the least radius of gyration. K is the effective length factor, which is 1.0 in our case. because both ends is hinged. And then you have the value for the length. The column is 5 meters long. So converting this to mm, this would become 5,000 mm. All over the least radius of gyration between 100 mm and 50 mm, we choose 50 mm. And this would give us a value of the slenderness KL over R of 100. Okay. So for the formula, using the formula for the critical stress, F sub C, that is equals to pi squared. According to the problem, the modulus of elasticity is also given 200,000 Newton per millimeter squared, all over KL over R, which is 100 squared. KL over R squared. And therefore, we will have, by computation, will you please also calculate if I have the same value as yours? 197.4 unit is Newton per square millimeter. But this is not yet the answer. What we are going to determine is the critical load. From the basic formula, stress is equals to load over area. Critical stress multiplied by the area is equals to the critical load. Okay. So that would mean we have, if you are going to determine P sub C, you simply multiply the critical stress, 197.4 Newton per millimeter squared, multiplied by the area. Okay, so the area is 8,000 square millimeter. 8,000 square millimeter. And that would mean we have the unit in Newton. Let me calculate. Will you please let me know if we have variable, we have difference in my calculation, huh? Okay. 1,579,200 or 1,579.2 kilo Newton. Okay. That will be our answer. 1,579.2 kilonewton is our critical load. Meaning, if you are going to